Hello, everyone. It's a pleasure to be here in this conference. So thank you all of you for coming to my talk. And today, I'm going to talk to you about TornadoVM. But before that, I'm going to motivate why we need this type of technologies. So heterogeneous hardware now are everywhere. Your smartphone contains a multi-core CPU plus a GPU. Your laptops contains a multi-core CPU plus an integrated GPU that is inside the CPU, plus, quite likely, a dedicated GPU. Even more, some companies, some data centers are attaching to their systems clusters FPGAs to increase performance and decrease energy consumption. Even more, some companies, what are doing is they are developing its own custom hardware for running custom workloads. And this is a famous case. For example, Google. Google has implemented its own processor for running TensorFlow. It's called TensorFlow Processing Units, TPUs, for running in a more efficient way TensorFlow computation. So quite likely, in the future, we might find more and more and more custom hardware. Okay. And why is this? This is because we have reached what is called the end of the Moore's law, okay, in which transistor size it cannot scale anymore, or it's difficult to scale, but it's kind of growing. But instead of frequency, it has been flat for a few years already. So in order to continue to increase performance and save energy, what companies are doing is to get custom hardware. Okay, that's the hardware side, okay? Now we have to use them somehow, right? So we need a programming language, we need a programming model, tools, compilers, and so on. So it seems like for every new hardware, we have a new programming model, a new compiler, and so on and so forth. And by the way, most of them are created based on C, C++, or even Fortran. But we know, and especially in this conference and in this community, that not all programmers are using C, C++, right? They tend to use high-level abstractions, Java, R, Python, JavaScript. So now the question is, if I want to use those hardwares, the new ones, how can I access from high-level languages? Well, right now, you have to use a library, okay? But there is no such a thing to run from high-level language in a transparent manner to heterogeneous hardware as the same thing like JVM, for example, targets optimized CPU code. But there is no JVM that targets optimized GPU code in a transparent manner. And that's where TornadoVM comes in, okay? So TornadoVM is focused on Java, and is defined as a plugin to OpenJDK that allows you to automatically run Java programs on heterogeneous devices. And this includes multi-core CPUs, GPUs, and FPGAs, okay? Even more, with TornadoVM, you can automatically migrate execution from one device to another. How cool is that? Okay, so for my talk, I'm gonna introduce some, some terminology, just to be all of us on the same page. And then I'm going to jump to the main section. I'm going to show you how TornadoVM is programmed, how we can compile code, how can we migrate execution context, and so on. And then I'm going to show you some performance results. Before that, just a quick introduction about myself. So I'm now a postdoc. I'm Juan Fumero, by the way. I'm a postdoc at the University of Manchester in the UK. I'm the lead developer of TornadoVM. And before that, I did my PhD at the University of Edinburgh in the UK, also working on GPU compilation for dynamic languages, or interpreter languages, using Graal and Truffle. So my PhD was not Tornado, it was something different. But what we're doing now is taking ideas we implement in that project into TornadoVM in a cleaner way, let's say. I've also done a few internships in Oracle Labs and CERN. As you can see, my background is mostly focused on parallel computing, heterogeneous computing, and compilation, JIT compilation. Okay, so let's go to business. Question, why should you care, or why should we care about heterogeneity, about heterogeneous devices at all? To answer that question, I want to motivate the answer by showing this graph. So I show you three different architectures: CPU on the left side, GPU, and an FPGA. So let's look at the CPU, the left side. And this is the Intel microarchitecture Ice Lake, 10 nanometers. And assuming you can get all the power that this CPU has, which means 8 cores plus vector instructions plus the GPU that is integrated, you can get up to 1 teraflop of performance. 1.1, 1.2, 1.3, depending on the chip. Now, let's look at the GPU. Now, one thing I want to highlight is we don't have 8 cores. In this architecture, Pascal microarchitecture is already 2 generations old from NVIDIA. We physically have 3,500 cores. And that gives you a performance of up to 10 teraflops, okay? And a similar situation applies for FPGAs. So in my talk, I'm going to talk about a lot about GPUs and FPGAs. So I think most of you are familiar already with GPUs at least, but just in case, I'm going to show you a little of introduction of this. So GPUs stand for Graphics Processing Unit, GPU. And it has been traditionally used for rendering and computer graphics. So to do that, GPUs implement a complex pipeline inside. So it's this pure architecture. And some of the stages in the pipeline are, for example, computing geometry, computing textures, computing, this kind of stuff. And some researchers and industry realize that some of the stages in that pipeline can be used for general purpose computation. Okay? Not only for computer graphics, but something more generic. And that's where CUDA and OpenCL come from. So CUDA and OpenCL are programming languages and programming models to use to program those devices in a generic way. That's one thing I want to highlight. So one thing, if you want to use it, you can run CUDA, OpenCL, but that requires that you have to know the programming model. And that's fine, you can learn it. But I want to also highlight that to use those devices in an efficient manner, you have to know architectural details. Okay, that's a requirement. For example, these GPUs, for example, L1 cache is not coherent, right? If you are sharing data and it's in L1 cache, you have to introduce barriers manually. So this is up to the programmer. If you don't do it, the results are wrong. Another example is you have to know how the GPU schedules threads, because by knowing this, you can tune the amount of threads you can run, and that can give you much better performance. Right? So don't take this slide as a tutorial for GPUs. I just want to highlight that apart from the programming model, knowing architectural details is a requirement. Okay, let's switch now to the FPGA, and I believe this is more unknown, at least in this community. Who knows FPGAs already? Okay, more than expected. Okay, if you don't know, don't worry. You don't have to if you use Tornado. But nevertheless, I'm going to explain to you. So, FPGAs stand for Field Programmable Gate Array. What does it mean? Well, it's a device that is attached to your PCI Express, and there is nothing after manufacturing. It's up to the user what to run there. For that, the FPGA provides what is called logic slides, like lookup tables, gate AND, OR, SHOR, just going back to college, this kind of stuff, and flip-flops to store bits information in there. You can also use block RAMs and DSPs, that is a specific hardware for running math functions, fast math functions. So, in a sense, it's like physically wiring your program into hardware. Okay? So, how is this program? Let me give you an example. Traditionally, there are a few languages. This one is called VHDL. And I want to show you how to do A plus B. It's half adder. It's not even a full adder. You remember, half adder is a short gate plus an AND gate. And that's the VHDL, how the code looks like. I'm not going to go to the details, right? You have to define what's your input, what's your output, and then you have to define what to do with your input and output. In this case, we want to do a short gate with the inputs and then the carry for the AND gate. And then you compile this to physical, hardware. Okay, good news is, fortunately, main vendors like Intel that provides FPGAs and Xilinx, they are providing OpenCL for that. Okay, so instead of doing VHDL, you can program in OpenCL underneath. Why am I telling you this? Because, spoiler alert, Tornado targets OpenCL underneath. What does it mean? It means that we can physically wire your Java methods into hardware. You don't have to program in VHDL. How cool is that? Okay, so the idea with Tornado is to potentially use all hardware available in your system. And here I show you a high-level overview. You have a multi-core CPU with multiple levels of caches. Okay, this is a representation. And the CPU is connected with Northbridge. It's normally inside the CPU. And the Northbridge is the one that has access to the main memory. And GPUs and FPGAs are attached to your system normally via PCI Express. Okay? So one thing I want to notice is they don't share memory, which means that if I want to use it, I have to allocate a buffer on the target device and perform data transfers. There is an exception for this, that is, the GPU can be integrated inside the CPU. For example, Intel integrated graphics. In that case, the GPU will be in the Northbridge or close to the Northbridge. Okay, so right now, if you download Java, OpenJDK, whatever implementation, you have something like this. You have Java, you are running on top of a virtual machine, and if you Git the code, the Java virtual machine can Git the code, you might target optimized code for only CPU. If you want to use another type of hardware, you have to use a library, or you have to do it by yourself, by crossing boundaries, JNI, or whatever other library. What we propose is this. It's what we call heterogeneous virtual machine. So we target Java for now, but in the future we might target other type of languages. In fact, we have prototypes for R and Ruby. And the idea is transparently target and use heterogeneous devices in a transparent manner automatically. Right? So with that motivation, let's go to TornadoVM. And first of all, I'm going to show you a demo. Okay? Before going to the details. This demo is called Kinect Fusion. It's the Microsoft camera. I think you might hear about that, right? So the goal of this application is to render in real time the whole room. What do we mean by real time? So human perceives real time around 25 to 30 frames per second. So we set up the quality of service to 30 frames per second. And this application is purely written in Java. And I'm going to show you, it's around 7,000 lines of Java code, okay, underneath. And I'm going to show you 3 different setups. First of all, running with OpenJDK, and then enabling Tornado to run on multi-core, and then Tornado on the GPU, that is in this laptop. Okay, so just one thing before going to the demo. The left-hand side is the input, the right-hand side is the output, okay? So the Kinect has different configurations, like light scene, depth scene, that's the inputs, that's the left side. Okay, let's go to the simulation. Right, I start running. I recorded this yesterday, by the way, just in case. So, first of all, just pure Java, and let's see what's happening, what's gonna happen. Trust me, the application is already running. It's extremely slow, okay? So I get eventually, you're gonna reach Git compilation, and you can get up to 1.7 frames per second. It's extremely slow. So what I'm gonna do now, yeah, it's very slow. So what I'm gonna do now, I'm gonna stop the application, and then I'm gonna enable Tornado to run first on the multi-core, okay? This machine has 4 cores, 8 cores with hyper-threading. So let's see what's happened. Hopefully we see something faster. Let's see. So I hope you can notice it's slightly faster. It's actually, we are rendering 4 frames per second, 4 core machines. Not that bad, right? Can we do it better? Okay, so let's switch now to the GPU. That's the GPU is in my laptop, 1050, NVIDIA 1050. And within a few seconds, voila, we can render the whole room, okay? And it's pure Java code, no libraries. Okay, so I hope I motivate you why we want, or you might want to use these kind of frameworks. Okay, let's go back to the presentation, and now I'm gonna show you some details about how this is done. This is the software architecture of Tornado. We have a layer architecture plus a microkernel architecture, which the main component is the actual execution engine, the runtime. And on the top, we have an API. You might wonder, why do we have an API? So one of the reasons is we don't detect parallelism. We exploit parallelism, which means that we need a way to identify where the parallelism is located. And that's why we use an API. Nevertheless, the API, in my opinion, is extremely simple, okay? You can tell me if you agree later on as well. So the API is called task-based parallelism, in which each task is a reference to an existing Java method, okay? So we compile at the method level, like hotspot. But sometimes we want to compile at bigger scope. We can combine many methods at once in the same compilation unit. And that's what we call a task schedule. Basically, we combine many methods and create a single compilation unit that it's going to run on the one particular device. Okay, once we have this API, what we do is we go to the runtime and we have a data flow analyzer. Why do we have that? Remember the diagram, the graph I showed you at the very beginning, all these devices attached to your PCI Express? They don't share memory. If we can save data transfers, we can get speedups overall. So what we do, we analyze data flow across the methods, and then we optimize that data flow, okay? Once we have the data flow optimized, we generate our own bytecodes, that are Tornado bytecodes. Because we have our own bytecodes, we need an interpreter for running those bytecodes, and that's part of the execution engine. And one of the bytecodes is launch this method, this Java method. The first time we say launch, we call the JIT compiler, say, now let's compile this method to a specialized machine code for the target architecture, for GPU, for the FPGA, or multi-core. So for the JIT compilation, we extend Graal, the Graal JIT compiler. And for OpenCL, so what we do underneath is to generate OpenCL. We base on OpenCL 1.2. So I know this is very abstract. I don't pretend you follow all the details just because of this diagram. So let's go into the details of each of these components, okay? And let's start with API, and let's start within an example. And I show you here the canonical example for GPU computing, matrix multiplication. And as you can see, it's extremely simple. Just the typical 3 nested loops expressed with objects, and then do the computation, and that's all. One thing I want to notice here is this application is sequential. Okay? So the first thing we need to do is to annotate the code. We expose one annotation called @parallel. Why do we have that? Well, we use this as a hint for the Tornado compiler, but this is what we call relaxed parallel semantics, which means that the user told us that this loop might be parallel, but Tornado itself will check. If we cannot parallelize, we just bail out and execute the sequential one. So it's mainly used as a hint for the compiler, okay? And second thing, we need to identify, I want to execute or accelerate this particular method. We do this through the task schedule I told you before. And that's an object called task schedule, and we pass a name, could be any random name, foo, bar, whatever. And then we create a set of tasks, task.task, as many tasks as you want. Each task points to an existing Java method. In this case, we say, please task called T0 point to the class compute method mxm. And then the rest is just the normal parameter for a normal method invocation call. Nothing special in there. And then we need a way to say, because they don't share memory, okay, GPUs normally, and FPGAs are different memory spaces, we need a way to synchronize variables. And that's through the stream out. That we expect the result in a matrix C variable, so please, once you finish the computation, performs the data transfer to get the actual variable in the Java heap. And then we call execute. So how to run Tornado? We just type Tornado and you make class. In fact, this is because we are very lazy people, okay? Tornado is just a Java plus all the options to enable Tornado. It's another Java program, okay? But you don't have to type those options, you just type Tornado. Okay, so let me show you another example, MapReduce computation. And I show you this because there are other alternatives to Tornado you might have heard about. For example, APARAPI. APARAPI has problems to express MapReduce computation. And I want to show you how natural, how easy it is to express it with TornadoVM. So we have a class compute, we have 2 methods, map and reduce, and then, as I showed you before, we have a task schedule, very simple, and 2 tasks. One to point to the map method, one to point to the reduce method. As simple as that. I want to highlight another thing. You want to see a call called stream in and stream out. In my opinion, this is real stream computing. Java 8 introduced what they call Java 8 streams, but actually it does not stream, okay? I think the name, in my opinion, is misleading. Actually, as soon as you get your computation done or your stream consumed, you cannot reuse the same stream. You need to compile a new expression again. In the case of Tornado, we define the computation, and new data is coming in and out, in and out, in and out. That's real string computing. We have a lot of examples in a GitHub repository, so feel free. So, now I'm going to show you a live demo. I have told you everything you need to know to use Tornado as a user level. You don't have to know anything else. So, to show you that, well, I'm going to show you the M-body application. It's the typical application for GPUs. Basically, it's the simulation. You know, you have a set of planets, stars in a galaxy, and you simulate the next step. OK, so I'm going to show you the Java code. And I have a class called M-body, and I have a method called M-body. And here is the whole computation. That's the typical, you know, the Newton universal gravitational equation. Basically, that formulation is a mathematical formulation. And then the only thing we did is we annotate one loop with parallel. And I tell him, Tornado, please take this as a hint. This loop might be parallel. Second thing, as promised, we create the task schedule, and should be here. And I say, create the task schedule, create the task, point to this class, this method, embody, and pass the normal parameters. And then synchronize with the host these variables. I expect the output in these two variables. And then I call execute, right? So what I'm going to do now, I'm going to run it. I'm going to start running the sequential implementation. So I hope you can see on the bottom. OK, let me clear. OK, I'm going to explain what it is. I'm going to run Tornado. I pass the program. First parameter is the input size. I'm going to run 4,096 bodies. And I say run the sequential implementation, 100 iterations. OK? So let's do it. It's taking, OK, 200 milliseconds, 120. Still, it seems like it's stable in 120 milliseconds. This is a micro benchmark, OK? So be aware of that. That's to show you a quick demo. Right, and 100 iterations had finished. Now, let's run with Tornado and see what happens. Boom, finish. Each iteration is 1.2 milliseconds. So it's 120x speed up. And I'm running this on my laptop, OK? This laptop. You can say, yeah, Juan, I don't trust you. This is not possible. OK. We can have a debug info and say, please, Tornado, give me in which device you are running. OK? And say, hey, you are using the NVIDIA 1050 GPU. I can say, actually, I can change the device. I don't have to run on this device. And we have an option in Tornado called Tornado Devices. Oh. And in this case, Tornado has the view of 4 devices. The first one is an NVIDIA GPU. It's actually the default device. Then we have an Intel CPU. If we use Tornado on CPUs, we're going to use multi-core by default. Okay? Then we have also the multi-core, but with different driver. And then we have an Intel integrated graphics. So let's do that. Let's change the device. Remember that I give names to the task schedule, right? And that's why the names are useful. So I can say, please, the task called S0T0, run it on the device 3, which is the integrated graphics. And I run with the debug option as well. Now running on the integrated graphics. Also, you can see, let's put just one iteration. You can see, because we generate OpenCL code underneath, so you can actually see that code. I say print kernel. That's the code, the ugly OpenCL code we generate for you. Okay? Cool. So from the user perspective, I think you are experts now in Tornado. Now let's switch to the internal details. Okay? So how this is done? Well, first thing I show you, you annotate the code, and then you compile with standard Java-C. There is no modification in Java-C. And then we plug in Tornado. Actually, Tornado is just Java program with the Tornado flags. That's all. We have a few components, the Tornado runtime and the data flow analyzer. I will give you details later on, so don't worry for that. And one of the main components, is not the only one, but one of the main components is the JIT compiler. And for that, we extend Graal compiler. We use Graal as a library, and we have actually our own nodes on top of Graal nodes, our own compilation phases on top of Graal phases, and so on. And I want to highlight this. Another alternative, like APARAPI, they do a direct translation from Java bytecode to OpenCL without any optimization. What we do instead is we are fully integrated in the Graal compilation pipeline. What does it mean? We can pass escape analysis, parcel escape analysis, loop unrolling, constant propagation, plus you have a loop that might be parallel, remove that loop, put a global ID, get global ID in the OpenCL world. We have a reduction, we know how to do efficient reductions on heterogeneous architectures, and so on and so forth. So we mix typical JVM, Graal optimizations with our own optimizations, and that will give us much power. So we have different stages. I'm not going to go to the details of the compiler level. If you know Graal, you will recognize these phases. And at the end of the optimization phase, after low IR, we generate OpenCL code. So it's as easy as traversing, it's a visitor. We traverse the Graal IR and generate OpenCL code. You can plug in any other backend. Why do we generate OpenCL? Because with OpenCL, we can target CPU, GPU, FPGAs, and multi-core, okay? We are also investigating PTX backend. PTX is like LLVM for NVIDIA, which theoretically could give us a bit better performance, but only for NVIDIA. Okay, so once we have the source, we call the driver. If we're running on NVIDIA, we call the NVIDIA driver and say, give me the PTX back, and then I get the binary, and then I install in the code cache. Then second time I encounter the same expression, I just get it from the code cache. Okay. Cool. So let's go deeper into more details. One of the key things we do, actually this is one of the things that keep us busy most of our time, is to do compiler specializations. Why? OpenCL is a standard. Code is portable. Performance is not portable at all. Which means that if we want to maximize performance, we have to specialize the code depending on the architecture. Which means that the code we generate for GPU is different than the code we generate for the FPGA or the CPU. And I show you here an example. You have a vector addition. This is the Tornado IR, which is actually Graal IR plus Tornado nodes. Don't worry, you're not supposed to read what is inside, it's just an example. And what we can do is, we encounter a loop, we can specialize the loop depending on the architecture. We say, you're targeting the GPU. Let's use what is called fine-grained parallelism, which means each thread is going to compute its own data item. If we use the CPU instead, we can say, specialize the code to use coarse-grained parallelism, which means that each thread is going to compute a range of elements. Okay? And those little tricks can give us a better performance. I show you here the specialization in Java code, but actually what's happening is all these transformations are directly in the IR, okay? In the Tornado IR. Right. Let me tell you another specialization, in this case for FPGAs. And if we don't specialize the code for GPUs, okay, we might be a bit slower, but still it's going to be fast enough, okay? However, if we don't specialize the code for FPGA, we don't get speed ups at all. Actually, we get slows down. So specialization for FPGA is a requirement. And I show you here a few examples of what do we do to get performance. So here I show you the intermediate representation in Tornado that corresponds with the Java code on the left-hand side. If you know Graal, you will recognize many of these nodes already. So one of the steps we do is we introduce in the IR parallel information. For example, how many threads you want to run. I want to run in this block of threads, 34 by 34, 64 by 64, things like that, okay? Then we can define the loop unrolling factor. So I know Graal has a phase to do the loop unrolling, but for the FPGA, it's not good. No, it's not good enough. So we can actually define our custom loop unrolling, and that will save us some space on the physical space on the FPGA. And that little thing can change this whole story to get performance. Another type of optimizations we apply is loop flattening, for example. If we have multiple loops, we just flatten all of them in the same loop. Okay, so if we don't specialize the code, that's the red box in the middle. That's the OpenCL code we generate if we don't specialize. If we specialize, that will be the OpenCL code that we generate on the right-hand side. As you can see, the yellow is, for example, thread attributes, loop unrolling factor, and so on. So if we don't specialize, we can get up to maximum performance of 5x only in 4 core machines. I mean, fine, whatever. It's not that impressive. However, if we specialize, we go up to 240x on the FPGA, just by doing these little tricks. Okay? Now you had 4 core machines, so the core machines, 240x. Now you might think to use the heterogeneous hardware, right? Okay. I want to tell you a bit more about the FPGAs. So FPGAs is not as easy as I show you. The compilation time is much longer than a normal compilation time. For example, GRAL and OR compilation pipeline for GPUs takes around 200 to 300 milliseconds to compile the code and specialize the code, including the calling to the driver. However, compiling to the FPGA, guess what? 1 to 2 hours of compilation. Why? Because we need to transform, actually we call the Intel driver directly, that's the VHDL or FPGA world. Why? Because VHDL, so OpenCL is transferred to VHDL. VHDL is creating a map of gates and routes, okay? A routing is called netlist. And then that netlist with this virtual has to be physically mapped to hardware. That process takes hours. So Tornado, for that, we have 3 different execution modes. We have what we call full JIT, so we spawn in background a new thread, and we compile for you. When the code is ready, after 2 hours, we switch. If you don't want that, because you have low latency requirements, we have ahead of time. So basically, when you pre-compile the bit stream, the bit stream is like the binary for the FPGA. And then, with the second run, you just load it. And that's fast, okay? That's a matter of milliseconds. Then we have another mode, which is quite interesting. You can debug using the FPGA with Tornado, which means that you are in your happy life with your Intel IG, Eclipse, your favorite IDE. You just press emulation mode, and you can debug what's going on the FPGA. Okay, so I'm going to skip reductions. I'm going to jump to something more interesting. So it's increasing, right? Trust me, good things are coming. So TornadoVM, we define it sometimes as VM in a VM, or a nested VM. Why? If you use Tornado, but you don't have your task schedules defined, you trigger the normal compilation pipeline. The interpreter mode, then if you use CRAL or C1 or C2 or hotspot, you just get, eventually you're gonna get the efficient machine code for that. However, if you have your running Tornado and you have your task schedules, you're gonna trigger the Tornado compiler. You're gonna build the data flow and the optimizer, and then we generate new bytecodes. And then we have our own interpreter, and that's what we call VM in a VM. Why? Because we manage execution, we manage compilation, we manage memory, and we manage task migration. That's a component to perform live task migration between devices. So this is very abstract. Let's go with an example, okay? So I'm gonna show you a trace. The MapReduce example I showed you at the very beginning. So just to recall, just a class with 2 methods, and then I have my object, task schedule, and with 2 tasks, one for map, one for reduce. I want to point out that first method, map, receives an input, and I use a temporal output that is going to be used as an input for the second one. But I don't need that variable back again, right? So we build the data flow that corresponds with the right-hand side. And the data flow is, okay, the input is your real input, and then the output is, yeah, you don't have to copy anything there because copies take time. So you just need to allot space, but I don't need it back, okay? That's what the data flow optimizer will tell us. And then we have the computation defined. First method map, second method reduce, and then the final output. From this graph, we generate Tornado bytecodes. And it looks as follows. So for all the tasks that belong to the same group of tasks, task schedule, we generate a section of Tornado bytecodes. They are enclosed between begin and end, just to define some limits. And we pass an ID. The ID is the initial device in which you're going to run, okay? Device 0 is a virtual device. But it doesn't matter. We can change the device at any point at runtime. And then it's a very simple process. We just traverse the graph. We get the input. We say, for the input variable, please allocate space on the device, allocate the space on the GPU, and do the data transfer. For the second one, I don't need to copy anything. It's just a temporal output. Just allocate space for that. And then many of the bytecodes are non-blocking, which means we need a barrier to wait for them. And then we launch the first method. The first time we execute this bytecode, we JIT compile the code from Java bytecode, actually from IR, Tornado IR, to efficient OpenCL code. And the same for the rest. We allocate the space for the output, we launch the second task, and then we perform the final copy out blocking call. This, in my opinion, is a very, very, very simple way to orchestrate execution on heterogeneous devices. Why? Because we can do clever things practically without touching any line in the compiler or the runtime. Let me give you an example. We want to process 16 gigabytes of data on a GPU that only has 1 gigabyte. By the way, this is a typical thing. So main memory on CPUs are bigger than the memory, the amount of memory you might find on GPUs and FPGAs. And here's the vector addition. I use 3 variables. And the first thing I did, let's look at the left-hand side first. We introduce a call called batch. And I say, batch in 300 megabytes. We have 3 variables, so total 900 megabytes. They fit into 1 gigabyte. And then underneath, Tornado automatically will unfold bytecodes and will execute in batches. Copy in, execution, copy out, first batch, copy in, execution, copy out, second batch. I haven't changed the runtime, the compile at all, right? Even more, I can overlap computation with communication, which means that in the computation stage, I can start copying the next chunk, okay? But that's transparent for the VM perspective. Okay, it's getting more exciting. Now I'm going to explain to you how we can migrate execution. So what do? We spawn, Tornado spawns a set of threads. How many threads? It depends on how many devices you have visible in your system. So we spawn a thread per device. Plus, we spawn also a thread to make progress, a sequential implementation, just run the normal programming hotspot, OpenJDK or whatever, just to make progress in the execution. Because we don't know that by switching, we are going to run faster. That's the goal. So what's happening underneath is each thread has an instance of the TornadoVM, okay? Which will compile and specialize the code for each device. And then we have a component called decision logic, and this will tell us, yeah, I know you are running with hotspot in the sequential thread, but if you switch now to this device, in this case the GPU, you might run faster. Now, question, how do we know? How do we make this decision logic? We introduce policies, okay? And we have 3 for now. We call it end-to-end performance, peak performance, and latency. What does it mean? So end-to-end performance will encounter in the decision logic, will encounter JIT compilation plus transfers and execution time, okay? Peak performance will not encounter JIT compilation and will do a warm-up phase. This is useful because, for example, in the case of FPGAs, it takes some time to get the right voltages to go to high speed, okay, to high performance. These 2 modes wait for all threads to finish, for all devices to finish in order to make a decision. That's why we introduce a 3rd mode called latency, which means that the first thread to finish, the first device to finish, just switch over it. There's one exception. Remember that JIT compilation on FPGA takes 2 hours. So when we use policies, we use the pre-compiled one, okay? Because otherwise it's not fair comparison. Right. And I want to introduce now what we call a new level of tier compilation. So you are experts on JVMs, most of you, so you know that when you start running on OpenJDK, let's say, on hotspot, you start running on the interpreter mode, and if the code gets hot, eventually, you're gonna get different tier of compilation. Once you get the maximum tier, let's say C2, or could be Graal, can you get faster? No. You just reach the maximum level of performance you can get. However, if we plug in the dynamic reconfiguration, we might get something faster after all. That's the whole idea. So, what I mean by this is, Tornado philosophy, we don't want to replace C2. We don't want to replace Graal. We want to complement those compilers. So, GPUs are very good for exploiting data parallel applications, and FPGAs are very good for exploiting pipeline parallelism applications. If your application follows those patterns, by switching to the right device can give you better performance. If your application doesn't follow those patterns, just stay with hotspot. They do a very good job, okay? That's the whole idea. Actually, there is no a single hardware to run everything efficiently. That's the point. Okay, so let me tell you a few things about memory management quickly. To talk about memory management, I will need another talk, but that's actually a very big component in Tornado, because JIT compilation is just one part of the equation. If you don't manage data appropriately, you don't get performance. So Tornado will take care of consistency and will take care of data transfers in a fast way for you. And what we do is, let's say you have 2 variables, A and B. A is used as an input, B is used as an output. And then, normally, of course, the Java heap, you will have those variables represented in there. What we do is we have a duplication of the heap. It's not the whole heap, it's just the device heap, or for each device. And then we copy those variables. And then the TornadoVM will keep consistency for all variables. We say that, the winner, for example, you switch to the GPU. Please update all references all the time between the Java heap and the output from the GPU, okay? But that's automatically managed by TornadoVM. Okay, so let's talk a bit about related work. And you might hear about Sumatra, perhaps, Aparapi. There is one other compiling production, it's called IBM GPU JNI. So Sumatra, well, it's a dead project now. I think Aparapi, some people are actually using it. They expose an API, it's not automatic, and actually, I think none of them can execute on FPGAs, with the exception of Aparapi. However, they don't know if by switching they're going to run faster, and that's the problem we solve with TornadoVM. So TornadoVM will switch to the heterogeneous hardware if their execution is going to be faster, okay? So we are kind of ahead of these projects. Okay, so let me show you something about performance. I'm going to show you the dynamic reconfiguration in action. Just to recall, dynamic reconfiguration is the ability of Tornado to dynamically switch device when it makes sense to switch. And I show you here 2 applications, DFT on the top, M-body on the bottom. And I show you different configurations. Dots, or circles, is I choose Tornado statically to run on that device. X-axis shows input size. Y-axis shows speed up against hotspot. So the higher, the better. Let's focus on DFT end-to-end policy, so top left for you. And as you can see, for small input sizes, TornadoVM will tell us, don't switch to the GPU. I know you have a GPU and FPGA, but don't switch it because it doesn't make sense. You're not going to get any speed up. However, by increasing the data size, by switching to the GPU, we get speed ups. And how much speed up? Well, we're talking about 4,000 speed up. This is logarithmic scale, okay? And the GPU is 1060, which is a typical GPU that kids play with video games, right? It's not that expensive. Okay, so let me show you this. Of course, we don't have speed up for all benchmarks. And I show you here a few of them. For example, SaxPy. SaxPy is the you have a huge amount of data to copy to the device. You have 1, 2 operations to compute, and a huge amount of data to copy back. So for those benchmarks, don't use the GPU or don't use the FPGA. TornadoVM will tell us, let's stay with hotspot. For other benchmarks like Monte Carlo, multiplication, embodied, DFT, this kind of stuff, we get very high speed ups. Okay, we can run on integrated graphics, AMD GPUs, Intel integrated graphics, NVIDIA GPUs, multi-core systems. We have a few papers. Please check out for more details and more benchmarks. I'm going to switch now to some, obviously we have limitations, okay? Most of the limitations are inherited from the OpenCL perspective because we generate OpenCL underneath. For example, we don't have object support, okay? Except for a few cases, the ones we know the data layout. We also don't support recursion. On OpenCL, there is no way to express recursion. Also dynamic memory allocation or exceptions. We might support this in the future, but in my opinion, this is tricky, right? Because introducing this for the target device, for the GPU, it might slow down the execution. Let me give you an example. GPUs don't have branch prediction, which means that if I have to use all this logic, be table, support, and so on and so forth, on the GPU, I'm gonna get worse performance than I used to have, right? So by using this dynamic reconfiguration, I only switch to when the application, when the pattern is the right one for the target device. For future work, we want to explore more stuff like, as I say, most of our time is doing specializations. One of those we're working on, we have a PhD student working on this, is to exploit different level of tier memories, exploiting tier memories. GPUs, for example, have different tier ones, is global memory, local memory, constant memory, and private memory. And you can program all of them. I know Aparapi is the competitor. What they do is they expose an API to say, copy this to local memory. What we want to do is to do it automatically, right? Fully automatically. Also, we want to introduce energy policies. For now, we focus on performance. But imagine the following scenario. Switch to the device that gives you less energy consumption. Or, given this energy constraint, switch to the device that gives you better performance. Okay? That's very interesting, at least for the cloud. Okay, so just to finalize, how is this TornadoVM currently being used? So we are now running a European project called EData. And the goal of the project is to provide end-to-end solutions for running big data deployments on distributed and heterogeneous hardware. And it looks like follows. We use Flink, Apache Flink. And on the edge, on the compute node, we want to plug in Tornado. And by using that, we want to run typical MapReduce computation and automatically use the GPU or the FPGA we have on the edge. There are some companies using Tornado. One of those is Exus in London, and they're using Tornado for machine learning. And this is a nice use case. They are trying to build a machine learning model to predict, okay, the probability of a patient to be readmitted in a hospital. Okay, and that could save you money because you can predict the amount of resources you want for a particular hospital in the public health system in UK. And they're using Tornado for accelerating the training model of the machine algorithms they have, the machine learning algorithms they have. And so far, they have been training with 2 million patients, and they go from 2,600 seconds for the training phase down to 180 seconds. By using Tornado, okay? That's a very nice use case. Okay, just to sum up, Tornado is fully open source, it's on GitHub. We actually published last release last week. We also have Docker images, so you don't have to deal with drivers, CUDA, OpenCL stuff. If you want to give a try, the best thing is just to pull the Docker image and run it. I actually can show you demos later if you want to. Of course, I didn't build this by my own. That's insane. We have a team. We are growing. We are mostly in academia. But we are looking forward for collaborations. You are experts, right? And we're looking for collaborations either industry or in academia as well. So if you're interested and you think that TornadoVM can help you in some of the pipelines or whatever you are doing, please talk to us and let's see what we can do. To take away, I have shown you TornadoVM as a plugin for OpenJDK that allows you to run Java programs, automatically run Java programs on heterogeneous hardware. And this includes multi-core CPUs, GPUs, and FPGAs. And even more, I have shown you, I hope I convince you that I show you that TornadoVM can switch to the device when it makes sense to switch to the device, right? It's a fully automatic process. And I show you also that the concept of having a new tier of compilation in which we complement C2 or server compiler to get execution done faster by running on heterogeneous devices. And finally, I show you that we can achieve very high speedups. We're not talking about 1x, 2x, we're talking about 1000x speedups. And with that, I conclude my presentation, so I'm happy to take questions. Thank you very much for your attention.
In microphone.
Thank you for presentation. From your code, I see that you're using 32-bit float porting arithmetic. Is it correct?
Sorry?
In code, you were using 32-bit float point
Yes.
arithmetic.
Yeah.
Is it possible to expose different precision? I believe it could give much better results for FPGA.
Absolutely.
And how it would look in the Java code?
So we support primitive, we map primitive in the Java side to OpenCL. So you can use any Java primitive, single, floating point, double precision, which is mapped to double in the physical OpenCL architecture.
What about exotics like 16-bit floating point arithmetic?
We can support those cases, yes. We expose a type in Tornado, I didn't talk about that, to do this kind of stuff, yes.
Okay, thank you.
Yeah.
No questions?
So in the code that you showed, you had an example, or you had your annotation that you could sort of give a hint to the compiler. Is it possible just to say, well, just take every loop and try and apply it? Because if you're going to analyze that, does it make any sense to do it to every loop rather than just the hints, or is it more sensible to let the developer give the hints?
Yeah. So it's possible. There's some limitation for that. So it's definitely possible. The answer is yes, it's possible. We don't do that for some reasons. For example, we can parallelize up to 3 levels of loops because OpenCL can get support for 1D, 2D, 3D. So if you put 4 loops, no, it's not going to compile. That's one thing. Second thing is Java defines very well what's going on with math operations, the reorder of math operations in floating point precision. And because we are taking the Java sequential code, the user is not aware, for some customers, they care about the last bit of precision, right? And by using that parallel, we are telling the user, be aware that this is sequential, but it's going to run faster, the semantics, but the precision might differ, right? The accuracy is the same because the standard, OpenCL standard follows the same as Java, but the precision might be different. Yeah. Did that answer your question? Yeah? Okay.